Okay. Hello. Good day, everyone. On behalf of the organizers, Pyro-Asia Forum and Frontier Laboratories Japan, I extend a warm and enthusiastic welcome to all of you and to our highly anticipated microplastics webinar titled Exploring the Newest Technologies for the Detection of Trace and Ultra Trace Levels of Microplastics in the Environment. We are delighted to bring together distinguished experts, researchers, and professionals from around the world to discuss one of the most pressing environmental issues of our time, microplastic pollution. This 1.5-hour session promises to offer deep insights into innovative analytical techniques, practical applications, and the future of microplastic detection, and followed by the monitoring. Our esteemed speakers today include Professor Silva, Dr. Karthikeyan Sathrugnan, Mr. Masahiro. We are grateful for your participation and interest, whether you are joining from Europe, India, Singapore, Malaysia, or elsewhere. Your presence today signifies a shared commitment to protecting our environment through science and innovation. Let's make this webinar an interactive and impactful experience. We encourage you to engage, ask questions, and take full advantage of the collective knowledge present here today. Once again, welcome. I am Anusha Kadimisetti, the Business Development Manager of Frontier Laboratories India. Today, I'm going to be the MC for the session. Thank you once again for joining us. Without any further delay, let me give a very brief introduction of what is Pyro-Asia Forum, from when it is started and how it is making impact on the society, everything. Pyrolysis Community Forum to connect Asian researchers and experts working in the field of analytical and applied pyrolysis and promote pyrolysis research for sustainability. So we yearly conduct symposium to strengthen our networking and collaboration. You can see the photographs of the Pyro-Asia, just started in 2020. The first Pyro-Asia has been actually hosted by IIT Madras, followed by 2023, and then the 2024 happened in IIT Guwahati. The next Pyro-Asia 2025 is going to be in December, hosted by the Thammasat University by the Chanatip professor. It is going to be in Pattaya, Thailand. We delightfully welcome everyone to join this Pyro-Asia 2025 and make it a huge success like the earlier versions. And before going to followed by the today's talks, I would like to give a very short introduction of Frontier Laboratories. What is Frontier Laboratories and how is Frontier Laboratories connected or been how it is jointly in this Pyro-Asia Forum for past couple of years. So Frontier Laboratories is a Japanese organization located in Koriyama in the Fukushima Prefecture. We are celebrating our 34th year of our successful journey in the pyrolysis technology. We are the global leader in analytical pyrolysis technology, and we are the monopoly and the manufacturers of pyrolyzer and peripheral devices and some UA columns. Today's session chair is going to be the Professor Tava Palaniswamy from Australia. Professor Tava Palaniswamy is a team leader at Environmental Plastic Innovation Cluster, the University of Newcastle, Australia. His specific research interests are emerging environmental contaminants, ecological and human health risk assessment, contaminant microbiome interaction. His ongoing research work is on ecological risk assessment of microplastics as vectors for contaminant transport. Now I hand over the session to Professor Tava Palaniswamy to take over the webinar from now on. Thank you.
Thank you, Anisha, and thank you, Karthikeyan, for this opportunity. And welcome, everyone. And so without further delay, I would like to introduce our first speaker, Professor Sylvia Lakoti. Professor Sylvia is a full researcher at the Department of Environmental Chemistry in IDA CASE. She holds a PhD in analytical chemistry and she leads an interdisciplinary research group in the field of analytical and environmental sciences. Her main research interest is to evaluate the presence and impact of organic contaminants, including microplastics, in the environment, and find solutions to mitigate the overwhelming problem of this chemical pollution. Today, she will be presenting about analysis of microplastic by GC Orbitrap MS. It's going to be a very interesting talk to hear about such an advanced analytical equipment. Professor Sylvia, please start your presentation and welcome to the forum.
Prof. Tawa, sorry, actually, there's small confusion. Maybe we have to change the order because just for the audience to understand, we will
Okay.
start with the ISQ. Okay, so first the single quadrupole, then MSMS, then Orbitrap. So maybe I think when we have lined up the speakers, it has gone other way, so that
Okay, that's
audience
fine.
can
Yeah.
follow the
Okay.
advance. So maybe I will be the first speaker, followed by Masahiro,
Fine.
then Professor
That's good.
Sylvia. Yeah, okay, sorry
Okay.
about this
Okay.
confusion.
No worries. Yeah. Anyway, Dr. Sathrugnan, again, another interesting analytical chemistry expertise. It's good that you are talking first, Sathrugnan, Sathrugnan, because you are also analytical chemistry background, and the topic you are going to talk today, microplastic analysis using Pyro-GCMS, which is my personal interest, and we are all waiting to hear from you. Please start.
Okay. Okay, so thank you. So I hope you all are able to see my screen.
Yes.
Okay, thank you very much. So, so good afternoon, good morning to all audience. Yeah, it's my pleasure to be again in this forum for sharing some of the developments that Frontier Laboratory has done for this microplastic research. Okay, so the first talk I will be sharing more on the single quadrupole ISQ based technique. Then my fellow speakers will be talking on other two domain, MS domain. Okay. So as you all know, because now the microplastic is a kind of mature topic, because you talk to anyone, they know something about microplastics, so that's a good thing. So because there's already a kind of ongoing research for more than 2 decades. So we have certain level of agreement or understanding on the classification. Okay, so as you know, the microplastics starting from 5 millimeter and below are classified as microplastics. Again, uh, under these European guidelines, we have classified that into two groups, like small microplastics and large microplastics. The large microplastics are 1 millimeter and above, and smaller one is 1 millimeter and below until 1 micron. Then anything below 1 micron, they are classified as nanoplastics. As you see from this slide, okay, so let me put my laser pointer. Yeah, because from researchers standpoint, we are interested in different size depending on what is our objective. Because when you are working on some marine research, okay, marine organism, then you can see even the large particles can have some impact. But if it is something human related impact, then they will be more interested in the smaller particles in the range of 10 microns and below, which can really cross the brain barrier or the cell invasion. So this is on the impact of like microplastic, where the size it matters. Similarly, when it comes to analysis, again, sizes matters. So depending on the size that we are trying to characterize, we have to choose the right technology for our identification and quantification. So particles like 1 millimeter and above, generally they can be easily identified by naked eye or some optical microscope, then supported with FTIR for the identification. So when the particles are of smaller size, like 100 microns and below, then yeah, people try to use it like microscope. And below 100 microns, yeah, people have to look for micro FTIR with ATR. Then below 20 or 10 until like 1 micron micro Raman. So this is how the kind of the state of the art for this microplastic analysis. So in this portfolio, we also see the contribution coming from the thermal analysis, where the pyrolysis GCMS is mainly used for characterizing these microplastic particles. So in terms of its limitation on size or kind of the particle size or the fraction, it is actually independent of the particle size, but each of these technologies has got its own pros and cons. So definitely this forum is not to really debate which technique is good or bad. Okay, so at the outset, we are all trying to improve our understanding on this impact of microplastic. So where we have to see these techniques complementary to really improve our understanding. Okay. So just for the benefit of some audience who have never heard about Pyrolysis-GCMS, a couple of slides I will be talking about it. Okay, I think on the left side, the micro FTR, ATR or micro Raman, it's a well-known technique because from the like beginning of this topic research, you can see many papers where they have employed this spectroscopic technique. So definitely people are aware of this technology. Okay, it is, yeah, the features, as we know, it is actually widely dependent of the particle size. Okay, and also it provides the morphological information, and quantitative analysis more on the number of particles per square meter, not the mass concentration. So challenges, as you go smaller in sizes, you may require longer analysis time. Also, the particle size and color will have some limitation
Excuse me,
depending on.
Karthikeyan, excuse me.
Yeah,
I think
yeah.
LinkedIn audience are not able to see your screen. They can only hear and present our cameras,
Oh,
not the
I
slides.
I see. And unfortunately, because this is first time we are trying there,
Okay,
so maybe,
okay,
yeah, we have to troubleshoot. Later, we will try to
okay,
play it
okay,
separately.
fine.
Yeah,
Yeah,
yeah, yeah.
okay.
Okay, sorry about that.
Apology,
Yeah,
apology to
yeah,
LinkedIn audience.
yeah, yeah. I
But
will do that.
you
Yeah.
can still type the questions at the end.
Yeah. Because it's the first time, maybe because we have provided a different link for video. Maybe which link they are using, I don't know. So
Okay,
maybe,
okay,
yeah, this
fine.
is first time that
Okay,
we are attempting.
thank
So we will also learn through this. Yeah. Yeah, anyway, so I will send the apology separately.
you. Okay, please
Okay.
go ahead.
Yeah. Okay. So on the right side, what you see is a pyrolysis GCMS, which I said before, it is independent of the shape and size and shorter analysis time, because GCMS always you run it for 30 to 40 minutes. And it provides the quantitative information, particularly for each sample, the amount in terms of the mass, okay, microgram or nanogram or milligram. Okay. Challenges, as you know, it is destructive. So if you don't do it correctly first time, then your sample is gone. And it does not provide you the morphological information. That's why I'm saying, so at this moment, I would say we need the both technique to complement each other, whereby we can have better information. Okay, so the typical output from pyrolysis GCMS is something what you see in this table, where you can get the absolute concentration of each type of polymer. Okay, but you also know, because based on the particle density and number concentration, you can also derive the mass. So this is how you can also compare that. Okay, so I just want to share how the research trend in a recent time. Okay, so we actually, one of our senior researcher has done some review on the trend of this microplastic research, and he found out, okay, so basically from 2018, the use of pyrolysis GCMS in microplastic is increasing, and it is drastically increased in like 2024 and above. Okay, so this is a very interesting information, I would say. That means the researchers are considering pyrolysis GCMS as an integral part of their research. So in terms of the matrices, matrices, you can see that it is applied or used across a different environmental compartment, also the human related samples, then few other sample which we have categorized as miscellaneous. Okay, so this is what the key message that I want to put it across in this webinar. So we need to complement our microplastic research by having a comprehensive characterization where pyrolysis GCMS will play an important role. Okay, so this slide further shows the different techniques within thermal analysis. As you know, there are different thermal analytical system that are employed, and where the Pyrolysis-GCMS coming from Frontier Laboratory is still a kind of market leader, where you can see many of the papers or the researchers have employed the Frontier Lab pyrolysis system. So other trend, what you see in microplastic is, because when you want to really assess its impact, the other missing information is more on the toxicity. So now the toxicological research also is gearing up. So where they try to look at the toxic effect of individual plastic as well as the mixed plastic. So this is very recent publications where they have looked into acute and partial life cycle toxicity of 3 polymer microplastic. Okay, so because as you know, sometimes they behave differently when they are like present in a single particle type, but when they have mixed plastics, so they can also have some kind of synergic impact. So it's not a benefit, it's impacts, where the toxic effect also more severe than looking at the individual toxic effect. So this is what this researcher have shown by looking at this copepod, like from egg stage to really to the adult stage, and they have estimated this LD50 and LD20 also. So one of the key observation is when you have a mix of 3 different microplastics, the toxic effect is higher than the individual one. So that's why in environmental samples we always expect a different type of like mixed microplastics, so which may have more impact than looking at the individual microplastics. Okay, now I'm going to take you through this pyrolysis GCMS technique, and also some of the R&D efforts that Frontier has done to really address these analytical challenges. Okay, so as I mentioned before, Pyrolysis-GCMS also is a part of this group of the thermal analytical technique. So where basically you apply this high heat energy thermal cracking in the absence of oxygen, and where you basically break down the macromolecule into micromolecule or small molecule, which you can pass through the GC for separation, and you get a typical chromatogram or pyrogram that can be used as a fingerprint for identification. So on the right side, what you see a typical pyrogram or chromatogram of polystyrene, which produce a prominent peaks for or significant peak for styrene, dimer, and trimer. Okay, so each of these peak comes with a kind of average mass spectrum, and instead of looking at each peak separately, we try to do its average mass spectrum of the 3 peaks for each type of polymer. Then this is how actually we do the identification, which I will explain it later. So yeah, so basically the Pyrolysis-GCMS allows you to do a thermal cracking to make these non-volatile polymer compounds into volatile species, whereby it also has high abundance in terms of the sensitivity, and you can use this chemical information through this extracted ion chromatogram, which are selective and sensitive, and that can be used like a fingerprint for identification. Okay, this is the simple schematic which everybody can understand, because GCMS is a kind of workhorse for environmental analysis for microorganic pollutants. So when you add this pyrolyzer to the GC, it also expands the capability of GCMS for microplastic analysis. As I said, microplastic in nature, they are non-volatile. So you need high temperature treatment in the absence of oxygen to really break down to make them as volatile, whereby GCMS can be used for analysis. So the key advantage of pyrolysis GCMS is the direct sample analysis, and also it can operate at high temperature, which is important for these microplastic like samples. So in terms of the workflow, it is very simple like any other environmental sample. So the first step is sample preparation, which I will discuss more in detail in next few slides. So once you have the sample ready, then you introduce your sample to the pyrolyzer. When you have more number of samples, you can consider a auto sampler. Then you produce a typical chromatogram that can be analyzed with the help of a software that we have developed, proprietary software, which allows you to really like provide you one-click solution for identification and quantification. In sample preparation, depending on the type of sample that you are analyzing, you have to consider a different pre-treatment procedure. Okay, for example, if it is something like a bioauto sample, yeah, or even a sample with organic matter, you have to consider the chemical digestion, followed by the density separation, and finally filtration. So no matter what is your matrix, at the end of the process, you have to bring them the particles on a filter paper, where you can choose a different filter media for different type of techniques. So when it comes to pyrolysis-GCMS, okay, we consider a cryogenic mill, which can actually powderize or pulverize the whole filter with the microplastics, whereby you can take an ellicott, because PY-GCMS is sensitive, so you don't need a bunch of sample which may contaminate the ion source and column also. So for certain kind of beach plastics and all, or in the sediment samples, or if you are doing a sea marine samples where you collect thousands of liters, right, you really have large particles, so which you can powderize and take a small ellicott. So the cryomill is a kind of accessory that can help you to homogenize the sample, whereby you can take small ellicott for analysis. Okay, so this slide just give you an overview of the different sample collection procedures. Okay, for water sample, yeah, either you do grab sample or plankton nets, and soil sediment, it's morely like sieving just to size segregate. Then for atmospheric air, you can use passive sampling or active sampling. For food and biota, basically it's a grab sample, then followed by you do some this freeze drying, milling, sieving, bring them into powder form. Okay, then pre-treatment, yeah, generally we have to do this digestion of organics by different way. So people have explored like acid digestion, alkali digestion, or the oxidative digestion with hydrogen peroxide and iron sulfate or the penton reagent, or also enzymatic oxidation. So different researchers have used different technique, but this potassium hydroxide, something you can see that many people are most commonly using. So then once you have the digestion completed, then you have to go for this density separation, and where again people have explored different chemical, but zinc chloride is something most widely used. Okay, and yeah, in terms of the filtration, alumina filter for IR and Raman, and glass fiber for or the quartz fiber for the pyrolysis-GCMS. So when you do it for pyrolysis-GCMS, even the density separation may not be required. After digestion, straight away you can filter and you can analyze the filter. There are some new developments happening where they're also trying to explore a different way of sample extraction using this pressurized liquid extraction, microwave assisted extraction, and cloud point extraction. So it also shows some interesting results for certain matrices. Okay, in terms of the analysis, yeah, I think if you are interested looking at the size, fraction, and number concentration, yeah, you have to go for this spectroscopic technique. And for mass-based analysis, yeah, pyrolysis-GCMS or TET-GCMS or thermal resorption with PY-GCMS and so on and so forth. Even like when it comes to nanoparticles, people are trying to use single particle ICP-MS also, but it's still under development stage. Okay, so let me dive through to some of the key things that Frontier Lab has developed. Okay, because since our interest is on quantification, we have come up with a calibration standard. This is something you don't find it in the market, because most of the standard suppliers, they provide a single plastics, certain particle size, and also pure plastic. So when you want to really develop a calibration for smaller concentration, you have to do some dilution in terms of dissolution and dilution. So here we try to make a blend of 12 commonly used polymers, okay, which are mixed with a diluent like silica or calcium carbonate, whereby you can use normal analytical balance. This blend actually has got 98% of silica or calcium carbonate, only 2% mixture of different microplastic particles. So whereby you can use normal analytical balance to weigh around like 4 milligram, but the absolute concentration of these plastics are in microgram level. So once you do analysis of this 12 different polymer, the different typical output pyrogram will be something what you see in this screen. Okay, so as I said, in the past, people were trying to identify a biomarker for each of these type of plastics, and manually you go and look for the peak and identify and also quantify. Now, just to simplify this process, we have developed a software called FSearch MP. So FSearch is our trademark software available for 1,300 polymer. Same thing now we have extended. Okay, we have extended for microplastic analysis. So where you can do a single click solution for identification and quantification. So when you use our software, the typical output what you get is shown in this slide. So you can see the type of polymer present and what is the peak matching probability based on the retention index, and what is the quantity, then also the ratio, the distribution of different plastic within the sample, then area, retention time. So the LOQ, something you can like get it from the calibration data, which you have to manually enter into the software. Okay. So that's very useful software to make this the analytical data analysis in a much faster way. So I'm going to show some quick examples of different type of samples, then also some new developments for nanoplastic analysis. Yeah. So with that, I will be able to wrap up my talk. Okay, this is one example for quantification of marine microplastic in the surface water. Okay, so where Newton this planktonate is used, which collect only 350 microns and above. So generally thousands of liters of sample are passed through this. So that means definitely you are able to collect a huge amount of microplastic by this way. So you need to do a proper sieving and isolate them, then cryomal and analysis. Okay, so here the typical sample taken like 94 microgram of this sample can show a data for polyethylene and polypropylene. So almost you can see the mass balance also almost like 80%. So that means the particles what you collected are mostly microplastics. So this is another example where the beach plastics have been collected, then again homogenized, then the typical amount of this 94 microgram. Usually our recommended mass concentration is 0.1 milligrams, so 100 microgram. So that is sufficient to really get a good signal. Okay, so this sample we found the presence of polyethylene and polypropylene. They are in the order of like 68 microgram and 6.8 microgram. Okay, now the other interest is on the air quality side is the tire wear particles, which actually you can see a lot present in the air samples as well as the road dust. So here the analysis of road dust actually, which is done by one of our South Korea research collaborator, Professor Kim. And again, yeah, we can see mostly the road dust will show the presence of SPR and butadiene rubber and natural rubber. Okay, so the key benefit of working with this Pyrolysis-GCMS is you collect the sample, you analyze it directly. There are no other sample preparation required like density separation or any other purification. Similarly, this technique has been applied for microplastic in the air, where we have taken different particles like a gasket impact sampler, which is able to collect particles of different size. So as you know from air quality aspect, people are interested in PM10 and PM2.5. So each of these filter, you can take it out and you can just micro punch these black circles, and that can be analyzed directly. No other sample preparation required. So this sample particularly shows the presence of polypropylene, polystyrene, and SBR. Okay, now when we think of drinking water or human samples, their concentrations are much lower. Okay, so you need to have better sensitivity. So we have come up with a splitless sampler. Normally, trace analysis or ultra trace analysis is done with the splitless mode within the GC, okay, where the liner is different. But for this pyrolysis product, because they are treated at high temperature, the splitless liner has to use smaller flow rate, which leads to secondary reaction. So that means you are not able to use the GC splitless liner for pyrolysis of microplastics particles, and the pyrolysis will disappear due to secondary reaction. So we have to develop a kind of small module which actually do a kind of force splitless to transfer all these compounds from the furnace to the trap, with the help of suction pump. Okay, then this trap is pre-cooled at -196 to ensure that all these compounds are trapped here. Then after that, we switch the valve to run it as a normal GCMS. So this way we can achieve the splitless analysis performance by improving the sensitivity by 50 to 100 times. The same module has got additional features like solvent cut and a backflash. So backflash also is a useful option, because even though the analysis peaks are like eluted within 20 minutes or 25 minutes, you may have to run the GC even like post run 30 minutes to ensure that all the high boiling compounds are like eluted. So with the help of backflash, you can reduce your analysis time, also preserve your column and pre-column. So this is the typical performance check that we have demonstrated. Okay, so to start with, we have taken the solvent, okay, like hexane and some hydrocarbons like C11, C13, C15, which you can see keep the split as 1, and see how conventional splitless for solvent can achieve like 50. Same can be achieved for our new splitless liner. So this hexane generally is removed through the solvent cut. That's why you don't see it. All others you can achieve almost similar to the conventional splitless. So as I said, the conventional splitless cannot be used for microplastic because of the secondary reaction. Okay, so this is how the typical schematic looks like. So you have your micro furnace and auto sampler, and this is the pre-column that is pre-cooled with the help of the microjet cryo trap to cool down to -196. And this multifunctional splitless controller has got solenoid for a backflash and also for the suction pump, so which we can use it for the backflash as well as the suction. And yeah, then typically it reduces your sample analysis time and preserve your column, and can also produce a very good sensitivity. So compared to the splitless, the split analysis which provide 50 nanogram. So same, if you want to do it with conventional, the detection limit is increased because of the secondary reaction. So with our new splitless sampler, you can go 50 times better, 1 nanogram compared to 50 nanogram for polystyrene. And with SIM mode, we can go further 10 times improved sensitivity. So that's the benefit of this splitless sampler. So most of the low-level analysis require this splitless sampler together with Pyrolysis-GCMS. So here we show how this can really be used for real sample. Since this real sample coming from sediment which has high concentration, we have manually diluted to show that we can analyze the concentration in nanogram level. Okay, so to cater this low level analysis, we also have a new calibration standard that is called a low range, which is 10 times low in concentration compared to our standard microplastic calibration standard. Okay, so I have a couple of quick examples on this drinking water analysis. This is something we are working with on collaborator in Indonesia. So where they are trying to validate a method for drinking water, because drinking water in bottled water generally cannot afford to go for very high volume sample collection. So we wanted to achieve a detection limit that is suitable for 1 to 2 liters of sample filtration. So initially they have taken some microplastics, waste plastics, which they have ground with the help of our cryogenic mill, and they try to synthetically prepare the 100 ppb concentration with the particles of this 10 to 20 200 microns. And this is the mixture of 3 plastics, which this is the preliminary studies which is showing the recovery of 40 to 60%. So this is ongoing study. So what I'm trying to say with this splitless analysis, it allows you to manage a small volume sample filtration, which is important for drinking water or bottled water type of analysis. Okay, this is another research work done by one of our user, where because these days people talk about micro and nano. So here they have shown how nanoplastic can be analyzed by the Pyrolysis-GCMS. So when it comes to the particle counting and particle size fractionation, yeah, they have used different techniques called field flow fractionation. And for the identification and mass concentration, they have used Pyrolysis-GCMS. Okay, this is the typical output. Since they procured the nanoplastics from standard supply of PMMA and polystyrene. So they have mixed these two, and this is a typical pyrogram they get. And the interesting results is they have done some recovery studies of different concentration. So when they do the real bottled water spiked with 0.1 ppm, which is like 100 ppb, so they were able to get 60% recovery in terms of the fractional recovery by field flow fractionation, and 60 to 80% with Pyrolysis-GCMS. So this slide, just I'm sharing it to show that nanoplastics also can be analyzed by Pyrolysis-GCMS as long as you are able to trap them in any filter matrix. Okay, so to cater our analysis for low and ultra low, like ultra level, so we have now one more new standard that is under development, which will be launched soon. So if you are trying to quantify in the range of 10 to 1 microgram level, our standard microplastic calibration standard should be sufficient. So for low level, yeah, we have 10 times lower concentration, which is good for 1 to 0.1 microgram. And we have new one that is 100 times diluted from the principal one, which is good for 100 nanogram to 10 nanogram. Okay, so with that, I would like to wrap up my talk. So the key message I wanted to convey that the mass-based analysis should be integral part of the microplastic research to advance our understanding on its impact on human and environmental health. And pyrolysis GCMS, as I said, it is a workhorse for microorganic pollutants. So it is same way can be considered for microplastic analysis as well. So really to achieve the desired performance characteristics, so Frontier Lab has put some R&D efforts to develop this microplastic column kit calibration standard, also glass insert, and this software, which allows you to do the analysis in much faster way, which is important for large scale monitoring. Okay, to achieve nanogram level analysis, we have developed this splitless sampler, which can overcome the challenges of the conventional splitless GCMS analysis. So again, yeah, we have also developed a range of calibration standard that can be used for a different range of analysis. Okay, so with that, I would stop here and thank you all for your kind attention. I think, yeah, as per our plan, we will complete all three talks, then we will take questions. Okay, back to Prof. Tawa, Chair. Yeah.
Thank you, Dr. Karthikeyan. It was a great in-depth talk.
Yep.
Thank you. Goodbye.
Thank you. Bye-bye.